Okay, so the next paper is an experience track paper from Google. Is Effingo. There are two presenters. The first one is the first presenter is Christoph. He's a data scientist at Google, where he measures and optimizes cloud infrastructure. He's also an associate professor at the University of Warsaw, Poland. And the second presenter is Mikko. Mikko, I'm sorry. He's an engineering manager in Google Storage. He holds a PhD in distributed computing and root cause analysis of large computing environments. He builds data software that scales for the last 12 years. So please.
Thanks. Yeah, thanks. So I will. Hope it works. Yeah.
Raise it somehow.
You want me to stand here or?
Okay.
Okay, maybe I'll stand here. So I'll start with a story. We have Alice and Bob, and Alice films a movie, and Uncle Bob wants to see this movie. The only problem is that Alice lives in Alice Springs in Australia, and Uncle Bob lives back in Europe in Brussels. So the network latency, and as well as the geographical distance, is huge, right? So the standard way to get this movie is that Uncle Bob issues a HTTP GET request and gets the movie from Alice. But say that the movie is really good and Uncle Bob wants to see the movie again. And then the movie is really good, so Uncle Bob throws a party for the rest of the family, and lots of family members want to see this movie on their local devices, right? So we end up with repeated usage of these expensive undersea cables. So, but of course there is a better way. Uncle Bob, before the party, does SCP, copies the file to Brussels, and then serves this file locally for the rest of the family. There is yet another use case. Say Alice has lots of movies, and for some reason she wants to do some ML processing. For instance, do face recognition to index all the movies to quickly find the movies where Uncle Bob appears. And Uncle Bob happens to have an idling GPU server back in Brussels. So of course Uncle Bob can put this server in a container, I mean real metal container, not the one we usually speak about, and ship it all the way to Australia, but it takes at least 6 weeks. So again, there is a better way. Alice can use SCP, copy all the files back to Brussels to Bob. Bob does all the processing locally and just sends the results back to Bob. And in fact, these are 2 out of 3 of our most important use cases. The third one is backup. And it seems that SCP is sufficient. So you may ask yourselves, I mean, why we are here giving talk at SIGCOMM'. But in fact, the problem is much more complex and much more fun than that. First, we very rarely copy, from A to B, because all the files we store in Google infrastructure are stored on multiple physical servers for redundancy. And moreover, different file systems may use different encodings. For instance, Alice may use something like RAID, and Bob can use something like the simple replication. So SCP it's hard to decide how to do an SCP with from 5 hosts to 3 hosts, changing encoding in between. Then we have a very common use case to transfer from one source to multiple destinations. Like say you have a bigger family and you have Aunt Claire in Canada and Uncle Dan in Denmark. And if you transfer to multiple destinations, probably you want to optimize the route as well. So probably you want to not to use these expensive undersea cables to transfer first to Brussels and in parallel to Denmark, but you would do something like this, right? First you transfer to Europe, and then you use the local European one to transfer within a continent. In fact, this routing may change in time according to network conditions, according to costs of links. But I mean, so far so good. SIGCOMM does networking, does routing without any problems. The problem here is that we cannot depend on like a centralized router that coordinates all the transfers within Google network, because the key requirement on infrastructure software is something called cluster level failure domains. So if a cluster fails, this can affect only the software that runs on this very cluster. So say we have a router on any third cluster R, right, sitting in Romania, why not? And if this cluster fails, it would mean that all the transfers worldwide would suddenly stop routing. So we have to do routing in a distributed way. But there are also some constraints on the optimal routing. It might happen that the optimal routing would be store and forward. So we go first from Australia to the US, and then from the US to Belgium. But there can be there are usually some regulatory constraints. Like, for instance, in a family you have this cousin Jan in Iowa who happens to overshare everything that you share with him, and somehow things that you share with him end up trending on Twitter like the day after. So you tend not to share things with cousin Jan unless you really want to share things. So, and this is in fact what is our key requirement, that we can use only the data centers that are the destinations specified by our user. And also this infrastructure evolves in time. So we have more than 100 clusters around the world, meaning that there are new clusters switched on, old clusters that are disappearing, and new regions and new locations appearing, disappearing quite frequently. So we need to kind of make this routing very dynamic. And finally, there is scale. So far we have only one transfer, but in fact, we have billions of them. Our system is the standard system that Google uses for batch file transfers. So we process more than 1 billion files every day, coming from more than 10,000 users. So these transfers do not happen. So first they interfere between each other. So they impact the bandwidth, the one bandwidth, but also the ingress, outgress, the I/O. But they also share the network with other higher priority transfers, like immediate transfers for our user data. So everything is extremely dynamic. So clearly, SCP doesn't do the job, and that's why we end up with Effingo.
Yeah, so we've got Effingo. That is our internal service for copying files on our storage file systems, mainly Colossus. And it operates on all Google clusters. It was created initially about 15 years ago, and it scales all the time. We keep developing this software. We've got wide spectrum of users. So what my colleague said, we've got users just copying backups, maybe across the regions, backups of databases. It could be used also for copying backups to recover, but also just pure data replication to serve data closer to our customer. to reduce the read latency. So this service has cluster level failure domain, meaning that a client can be in any cluster and can request copying a file from any other cluster to any other cluster. What it guarantees also is, yeah, you see the arrows, great. So what it guarantees SLO for copies that are done quite cheaply, meaning using almost like lowest class of our network bandwidth. So not impacting user critical interactions like streams. And here's the simplified architecture of our system. And every color stays for just different data centers. So here we can see in total 4 colors. Cluster A is purple. Green is the destination cluster where we want to copy a file. Yellow is the source cluster from where we're copying. And then blue one is the cluster of a client. So client sends a request that is then routed and gets into the transfer manager that is in the source cluster. So because of the cluster ID in the file path, or maybe in some other flavors of the file system, it's in the file metadata or the properties. The system figures out where physically the file exists that will be copied. And then the entire orchestration flow happens. It's explained in details in our contribution. So the resources engaged are in the copying. So in the data plane is, of course, network bandwidth. And at the destination worker and source worker, we need memory, CPU. And, of course, we need to access read the storage. So reads and writes also are required. I mapped here a purple cluster because during the transfer, we can switch to alternative sources that we track for typically like last 14 days. And if a user copied some file that matches by checksum, we will take a file or just its chunks if the switch happens during the transfer, like you can see in the torrent, for instance, then we will take it from there. So that's like some usage statistics, typical day. We copy more than 1.2 exabytes per day, or all data centers, all users aggregated. It means that we've got typically traffic of about 200,000 files per second, like worldwide, all users. And our peaks can be like per user, per cluster, even half of all the traffic aggregated. So that's very challenging. That means typically all our resources, the components that you've seen before, they need to scale horizontally, vertically, and we need to avoid single point of failures. So that's the advantage of our system, that we regulate the throughput of a copy. So we copy files in parallel. If a user has like enough resources, like budgeted, then copying a file that has 1 gigabyte versus 100 megabytes will take the same time, because we will copy this file in transfer chunks that are about 50 megabytes each. And basically, we've got 2 algorithms to decide on how many transfer chunks can be copied in parallel, and then we use just workers to allocate them per transfer chunk. The advantage of this system is that when users are competing for resources, but they have just the same type of quota, so at the same priorities, or we've got a user that sends copies with the same priority. The aggregated throughput you can see at the top will remain stable as we attach to a particular link just different transfers, given that there are no constraints, for instance, on storage destination or reading from the source. That's like maybe more sophisticated example how we do fair splitting of the bandwidth allocation. And here we start just with the read transfer from source that can have egress maximum 300 to destination D1, right? And at some point, we start the blue transfer from source 2 to destination 1. And then we see the first split like 250 megabytes. And then we start the third transfer that gives 150 to the green and blue links and the maximum that can be allocated to S1 to D1. And what my colleague said, the important characteristic of this system as its internal file copying system, it's used by probably all other services in Google and the products you know, is that it gives compliance to these copies, to the data at rest and data in move, meaning that maybe there is regulation, you need to avoid certain localizations because, for instance, of European Commission law that you cannot move like data from France to US because of some particular agreements, and it makes sure that all the constraints are followed, but also leaves like a lot of room to our users. That's the summary, and we've got, I think, time for questions now.
Hi, I'm Matthew Grosvenor from Jump Trading. We operate networks at scale, large WANs, we move files around. So we face similar problems. We have regulatory issues, similar problems. What I didn't catch in the talk was what's the key insight? What's the novel step that you've taken here that makes this better than just SEP?
Decentralization, in one word. Radical decentralization. So the fact that you have and on multiple layers. First layer is coordination of transfers between managers that reside in clusters. So if you copy from A to B and C, you only talk between A, B, and C. And then when you have the optimal, the root design, there is yet another degree of decentralization with these multiple workers, and then they can be thousands of workers on each cluster. Each worker transmitting a chunk to each to an individual worker on the other side.
So would you say it's the planning of the copy that's the key difference here, rather than just executing it?
And yeah, but then during the execution, we also have this online feedback mechanism that dynamically adjusts the number of worker slots used for transfer, so that we efficiently use the available bandwidth.
Sort of application layer.
Yeah. As you said, as you saw on this plot with many lines that go up and down. No. Next one. Yeah, that one, right? So there is some dynamic. So for instance here, the conditions change. So this guy can recover to the full bandwidth.
Thank you.
Thanks. Thanks.
Well, I actually have a question. As an experience paper, I didn't see much operational experience here. So can you describe any failures you encounter? Or?
I think we can start. So, did we have this graph with the
Failures?
failures?
Probably no. No.
Okay,
Oh,
but
sorry.
it's in the paper. So it's included in the paper. I mean, first of all, we guarantee SLO for our users. Secondly, the error rate of copies, it's about 3%, and we publish that in the paper. This error rate root cause is typically like in a user, so maybe they are duplicating the copies and data already exists at the destination. And about the failures, the operational experience so far is that we take care about like reliability matters a lot, meaning avoiding single point of failures in every cluster, because our control plane has, for instance, two databases. One is to orchestrate and register current copies that are scheduled. And whenever you face a peak at particular cluster that you don't know it will happen, you need to scale this database somehow. That's one of the examples. Another example that we face is static sharding. So based on file name, we assign a particular task of transfer manager that orchestrates entire copy request. And here, for instance, our future work is on dynamic sharding and also like dynamic scaling of the transfer manager component. Then we've got also another database that we use. It's called Content Tracker. That stores historical copies per user for last like 14 days. That is used for copy tree optimization. So actually, what Krzysiek explained in the use cases before, avoiding this expensive cross-ocean links, when we can copy data to the continent and then propagate from there.
And I will also add something that does not show very well on curves. So there are also user stories. So for instance, like some teams had their own copy services, and because of the complexity of Google internal infrastructure, these services, I mean, it was expensive to maintain these services with the infrastructure evolving. So we had one team that basically tried to find a bottleneck in their transfer that normally, so you had a transfer that was done each day, normally completed in, say, an hour, and then they had problem because suddenly it started to take like 20 hours. And they couldn't figure out for a week like what happened. And with Effingo, similar, and it occurred that they lacked some kind of, you know, permissions, quota for I/O at one of the clusters, and they were using best effort, but this best effort was stopped being reasonable at this cluster because of other traffic. And with Effingo, there is like a standard user interface that shows you basically where the bottleneck is, and you can detect and resolve these administratory bottlenecks in hours.
I see. Thank you. Okay, so maybe we can go on to the next presentation.
Thanks.
Thank you.
Thank you.